We will show how defects are revealed by the shearography method, using this panel with drilled holes. Reinforced tape was glued to this panel. Here's a reinforced tape. We have certain areas in which there is air between the tape and the panel. This tape did not stick very well. We also see connection lines. Let's see how our shearographic device will reveal these features. First, we put the object in front of the interferometer and adjust the focal length. To do this, we remove the shearing. Now two images of the same object have matched. Then we set up the focus. Now we have the object's image in focus. After that, we make a shearing, for example, in the vertical direction. We change the value of shifting and see how one image has moved relative to the initial position. We can see two images shifted each other in a vertical direction. Here are the features associated with air bulbs between the panel and the tape. We observe an area of the plate from this to this place. Now we record the initial picture and turn on the live phase mode. Due to the change in air temperature by fractions of a degree, we immediately see the deformation of the surface of this area, which indicates a not very good bonding of the tape to the panel. Now we heat the object using the warmth of the hand. Often this heating is sufficient for such thin plates. Almost instantly, the regions where the tape hides the holes are revealed, since in these places, the deformation of the tape is much greater. In the area where the edge of the tape is located, the deformation with such heating is also very large. It is interesting to pay attention to the relative position of the dark and light areas. A dark area appears at the top of a defects region in the form of the capital letter D. Below there is the mirrored light area. After processing, filtration and unwrapping, we can see Let's apply one more filter. All these defects are revealed. It is important to note that we have a dark area on top of the defect region and a light one on the bottom. Now go back to the fringe viewer and change the shearing to the opposite direction. First, we remove the shearing and then move up the second image. We leave approximately the same shearing as it was before, but now the second image is shifted up. Previously, it was shifted down. We record the initial state. Turn on the live phase mode. And carry out heating. We see that now the relative position of the light and dark areas has changed. Now there is a light area on top of the defects. Previously, it was the other way around, there was a dark area above and a light area below. Now, like this. This shows that the shearing is in the vertical direction. And depending on how the differentiation is carried out, from top to bottom or from bottom to top, dark or light areas will be located at the top or bottom. Let's process the phase picture. Launch the Fringe Editor program, apply standard filtering and phase unwrapping. Now you can see the light areas above and dark areas below. Here we have a defective region. When heated, the surface bends towards the observer. Since optical differentiation occurs, if we calculate the derivative along the vertical line from above, it can be seen that in this zone the intensity is higher, and in this one, it is lower in comparison with the gray background without deformation. If differentiation is made from the bottom up, then for each defective area there will be a light area on top and a dark area on the bottom. Thus, with opposite directions of shearing, we get the same shape of the picture of deformation, but with a different sign. Time has passed. The heat after heating was distributed over the object and desponding defects between the tape and the panel were visualized. Defects in areas near holes are less noticeable compared to defects with air bubbles. Thus, depending on how the thermal loading is performed, different types of defects are revealed. To identify some types of defects, it is advisable to apply rapid heating. To identify other types of defects, it is more effective to use a gradual change in temperature. We carry out rapid heating, and again surface over artificial holes deforms much intense. Now desponding defects are less visible. Now let's see how the same defect will appear if we make a shear in the horizontal direction. First, we remove the vertical shearing so that the images are coinciding, and we shift one image to the side, for example, to this one. We see a shearing in the horizontal direction. Let's see the deformation of our panel. We visually see the areas with air between the plate and the tape. Click Set Reference, Live Phase, and Heat Up. The same defective areas are clearly visible. Very bright. Dark and light areas in the region of each defect are arranged in the horizontal direction. Whereas earlier the dark and light areas were arranged vertically, now they are arranged horizontally. This additionally confirms the presence of defects in these places. By the way, we see that the defective area here, at the edges of the tape, is no longer so distinguished if we compare it with images retrieved using vertical shearing. The edges of the tape move mainly in the vertical direction and slightly deform in the horizontal direction. We can see the deformation of this area, but it is not as large as it was when using the vertical shearing. Therefore, it is important to select the correct direction of the shearing in order to identify certain defects. Let's start the Fringe Editor program, do filtration, phase unwrapping and surface construction. You can see a very clear influence of each defect and also the edge of each glued tape. Now let's try to increase the shearing even more. As the width of shearing enlarges, the measurement sensitivity increases. With the same deformation, more fringes should appear. We increase the shearing approximately 2 times. You can see how shifted the images are. We carry out the same experiment. By the way, here you can see how large the shearing is. We record the initial state, turn on the live phase mode. We can already see how deformation waves begin to run. They have not yet begun to heat up, but areas with defects are already beginning to appear. Now our defects are clearly visible on the screen. However, unlike previous experiments, we observe that the distance between the centers of the light and dark circular areas has become larger. This is because we have increased the shearing and the areas of derivative extremes have shifted relative to each other. If you make the shearing even more, then these zones will expand even further. But the center of one of the regions will be in the same place, regardless of the amount of shearing. As the shearing increases, the distance between the center of the light and dark areas enlarges, but at the same time, the typical pattern remains when each defect is represented by dark and light areas. Every point is visible. Time has passed and the temperature has leveled off. The effect of these defects is practically invisible on the screen, but the appearance of deformation is observed in regions with a defect of the non-glued type. The gluing defect is most clearly visible in this place. We make a shearing in the opposite direction, moving the image to the starting position, then moving it further to the right. We register the initial state, turn on the live phase mode. Then heat up. Deformations during heating are clearly observed. The surface cools down quickly enough. Stopping registration. Sending data to the fringe editor program. Do filtering and phase unwrapping. A picture similar to the previous one is observed. But the dark and light areas are reversed. The shearing was changed and the relative position of the light and dark areas in the region of each defect changed. Let's make a shearing in both the vertical and horizontal directions. Now the shearing is set in the diagonal direction. We record the initial picture, turn on the live phase mode, heat it up. You can see that the light and dark areas are in a diagonal direction. That is, each black and white area is directed along with the shearing. Now we have installed a lens with a focal length of 50 mm. As a result, we observe a smaller area of the object, from this place to that. Approximately 5 cm. We see the same air bulb that was visible earlier. It is a consequence of the air being trapped between the tape and the plate. Now, as before, we will set the vertical shearing. By the characteristic patterns in the image, it is possible to estimate the magnitude and direction of the shifting between images. We record the initial state. Turn on the live phase mode. We observe the surface deformation in a real time during heating. We observe a smaller area, but each hidden hole shows up much better. There are 4 hidden points visible. Also visible is an additional area with a desponding defect. Let's heat it a little more. Then save current state and process it in the Fringe Editor program. One can see a uniform deformation field and defective areas against its background. Let's build a 3D deformation surface. You can see an influence of each defect on surface deformation. All these big defects strongly stand out against the background. There is also a small defect in the center.